Hello everyone and welcome to this presentation on drone audition for search and rescue. My name is Antoine Deleforge. I am an associate researcher with Inria. The goal of this talk is to give you an overview of some of the key challenges faced by this emerging topic and to highlight some of the recent datasets that have been made available for research. After a brief introduction, we will review 4 recently released datasets aimed at fostering research in this field and present some of the results that have been obtained on this data. We will then make a short focus on the task of Igor noise reduction before concluding the presentation. In 2014, the United Nations released a report on the use of drones in humanitarian response. The report acknowledged their unique capabilities for search and rescue, which already allowed quick actions during typhoon disasters in Haiti and the Philippines. The report encourages the development of such solutions while warning that their use should be reserved to natural disasters rather than conflict zones. Current solutions only rely on video or infrared cameras. Such sensors are limited in the presence of occlusions or bad lighting conditions due to fog or smoke. Distress signals captured by microphones embedded in a drone could constitute a critical and complementary modality to vision. That said, providing drones with audition comes with a number of challenges. Obviously, the drone's rotors constitute a very loud source of interfering noise, which we refer to as Igor noise. This noise is made even worse by the wind caused by the outdoor flying conditions. Finally, search and rescue scenarios typically involve fast movements and come with a strong need for real-time processing. Here are typical examples of drone audition tasks. Igor noise reduction consists in processing the signals obtained at the microphones in order to reduce the noise produced by the drone while preserving auditory signals of interest. Sound source localization is the task of estimating the direction of the sounds recorded by the microphone array, which is critical for search and rescue. Finally, a less studied and emerging task is to identify acoustic echoes in order to navigate the drone in challenging environments using echolocation, just like bats. Moving now to datasets. The ERA UAS dataset, published in 2018, gathers a number of outdoor embedded in-flight recordings from drones of different types. It does not include other sources than drone noise, but does include interesting multi-drone sessions, making it quite unique. The AVQ datasets, published last year, provides outdoor static recordings of 1 or 2 human speakers from a drone mounted on a tripod and equipped with both microphones and a camera, with annotated positions of sources. This is the only publicly available audiovisual drone embedded dataset to the best of my knowledge. Now let's talk about the Dragon dataset, which was released in 2018 by colleagues and myself. It contains indoor, in-flight and static audio recordings of a speech or a broadband source emulated by a loudspeaker. We used a quadrotor drone equipped with an H-channel microphone array, and the relative position of the source with respect to the drone is precisely annotated at all times thanks to a Vicon tracking system. This is the only publicly available datasets of in-flight drone recordings with fully annotated positions to the best of our knowledge. This video shows an example of recording session from the dataset. Note that the sound you hear is from the external camera, not from the drone itself, since I don't want to break your ears.
Glass heels are to be found in both high and semi-heights.
Don't ask me to carry an oily rag like that. The drunkard is a social outcast. Movies never have enough films.
I received a joint appointment in biology and the engineering department.
Positive results start when it goes towards the hand you use to make your mark.
The new suburbanites work.
Here are some source localization results obtained on this dataset using multi-channel Wiener filtering to reduce noise, followed by the GCC-FAT localization method. The red lines represent the ground truth elevation angle, while blue dots represent estimates. As can be seen on the left, good performances are obtained when the source emits broadband noise, despite a very low signal-to-noise ratio. On the right, we see that performance drastically drops when the source emits speech due to the strong overlap between drone noise and speech. Here are some further results obtained by the 20 international teams of students who participated to the 2019 Signal Processing Cup on audio-based search and rescue, which was based on the Dragon dataset. As can be seen on the left, The best teams obtain very good results on static speech localization. On the right, we see that performance drastically dropped in flying conditions, despite similar noise levels. The best team reached a 60% localization accuracy on this task, showing that there is still room for improvement. The best performing teams generally used a combination of trajectory smoothing, noise reduction, channel selection, speech activity detection, and used motor speed logs to predict the noise statistics. The last dataset I want to present is the SP19 Igor noise dataset, made by participants of the 2019 Signal Processing Cup. It contains embedded recordings of pure ego noise from 10 different auditory drone models, using different array designs and placements. The dataset reveals the diverse forms that drone ego noise can take depending on where the microphones are placed with respect to the rotors, their mounting, their number, and their strength. Let's listen to some of them. This is from the Chums team. This is from the Leeds UAV team. And this is from the Maverick team. Let's now look in a bit more detail to a typical drone ego noise spectrogram. This part here corresponds to stationary noise, whose statistics are translation invariant. Such noise can be easily removed using Wiener filtering, as long as the noise statistics are known. They can, for example, be learned in advance or predicted from the drone status. Here, for example, we see harmonics components coming from the rotation of propellers. A nice feature of those harmonics is that they can be predicted quite well from the motor data. Here, we see the average spectrum of ego noise when propellers are rotating at a constant speed of 80 rotations per minute. We can clearly distinguish peaks at 80 Hz, 160 Hz, and so on, corresponding to frequencies proportional to the speed of rotations. These could be used to estimate parts of the noise covariance matrix. Finally, this part here corresponds to wind noise. We see that it has high energy and strongly overlaps with speech frequencies. This is another example, this time with speech. There isn't much hope to reduce such noise, but it usually does not occur in all microphones at the same time. This suggests to automatically and dynamically detect channels corrupted by wind and ignore them while processing signals. In conclusion, search and rescue is an important and promising application for drone audition. It involves a large number of complex audio signal processing tasks and comes with its own challenges, such as dealing with a compact array near very loud noise sources and very dynamic soundscapes. This is an emerging field of research, recently fostered by the release of publicly available datasets. Please join in. Thank you very much for your attention. I'll be happy to answer your questions after the session.